Okay. So our today's speaker is Eng Keat Hng, who will speak about covers of cycles and paths.
So thank you to the organizers for the invitation to speak here today, and it's really my pleasure to be here today. Right, so as mentioned, I'll talk about minimum degree conditions for powers of paths of cycles. So the study of conditions for a host graph. So if you cannot hear me, please just sort of tell me so that I know. So the study of conditions for host graph G, container tile graph H, is a major program on stream graph theory and has been very extensively studied. And so one of the earliest results in this area is Mansell's theorem from over a century ago, which tells us that if a graph contains more than n squared over 4 edges, then it must contain a triangle. This is later extended by Turan to all constant size cliques, and later by addition stone to all graphs H of constant size. Now, while the Edderstone theorem resolves the problem of subgraph containment for all graphs of constant size, it's naturally interesting to also consider what happens when we allow the size of H to grow with n. And so in this direction, one thing to note is that if you want to talk about containing a spanning subgraph, if you have an isolated vertex in a graph, this would naturally be a bit of a problem. So usually what we consider is something called minimum degree instead of the number of edges. And in this direction, the well-known result of Dirac tells us that we have a minimum degree condition, namely at least n over 2, which guarantees for us a Hamiltonian cycle in the graph. Right, so there's been also work to extend Dirac's theorems to other bonus classes of graphs, and one direction in which this has been done requires the following definition of graph power. So we say that, so we define the case power of a graph G to be the graph we obtain from G by basically adding all edges between pairs of vertices at distance at most k from each other. And so to give you an idea how this sort of works, okay, this is not so good because of the cut. So on the left, you have an example. On the outside, you can sort of see a black ring of 6 edges forming a cycle on 6 vertices. And on the right, you have a path on 8 vertices in black. So that's something like this. Right, so if you want to get the square of these graphs, what do we need to do? We need to add edges between all pairs of vertices, which are at distance 2 from each other. And the red edges, which I'm not sure if you can quite see, these ones on top, and also the cross ones here, are precisely the edges you would need to add to do that. Right, so so Böttcher and Seymour can make the following conjecture. So the conjecture that every graph, if you have minimum degree of at least kn over k plus 1, then you will actually contain the kth power of a Hamiltonian cycle. And so note that if you put k equals 1, that's basically Dirac's theorem, because the first power is really just doing essentially nothing. And to sort of see how this is sort of the best possible minimum degree that you can hope for, well, okay, so throughout this talk, I often use examples when k equals to 3, just for the sake of concreteness. So here we have k equals to 3, and if we consider a complete 4-partite graph, which is almost balanced, just slightly imbalanced, like this, then what happens is that if you want to find the cube of any path or cycle, the way this will go is sort of the path or cycle, cube of path or cycle will have to sort of go around all 4 vertex classes, because every 4 vertices will then form a clique. And so at the end, what happens is that you at some point run out of vertices, because you use one from each of these, and at some point this will get used up, but yet you don't quite have your Hamiltonian path or cycle yet. Right. So Komrov, Hladký, and Semiradius were in fact able to prove that the Böttcher-Seymour conjecture holds, but only for very, very, very large graphs. So what they use is the regularity block method. So this combines the regularity lemma of Semiradius and something called the block lemma. And so one thing that you actually can get out of the proof as a byproduct of this method that they use is that not only do you have the kth power of a Hamiltonian cycle, you actually can get the kth power of cycles of many lengths. So literally from almost Hamiltonian all down to basically very small constant sizes. So this is a byproduct of actually this method that they use. Right, so on one hand, we have the Eddystone theorem. This gives us a solution for graphs of constant size. And on the other hand, you have the Dirac theorem and the Böttcher conjecture, which deal with spanning powers of cycles. So it's natural and interesting to consider what happens between these two extremes. Well, if you ask for something of linear length, but not really quite Hamiltonian or even close to being that. So this is precisely the sort of question that Böttcher and Hladký asked. So they asked is that 1 million degree guarantees that we have a kth power of a power cycle of any arbitrary given linear length that you might be interested in. And so, okay, for some minimum degrees, this is not so hard to resolve if you would consider minimum degrees delta up to k at minus 1 n over k. So again, using our example, k goes 3 up to 2/3 n. So this is sort of the sort of what I call the Turan threshold. So at this point, you can still construct these 3-part graphs. And because any cube of a path or cycle, which is of non-trivial length, must contain a copy of K4 in this case. So this sort of says that you cannot guarantee that these things exist at all in this regime. And so now we move on to the sort of more interesting range. So between k minus 1 n over k and kn over k plus 1. So between the Turan threshold and what the Böttcher minimum degree. So in this regime, we have 4 part-type graphs of this sort. So before k equals 3, 4 part-type graph. And so we have put an independent set here and here of size n minus delta, and put the remaining vertices in this smaller blob. So what we notice is, okay, so because every 4 consecutive vertices must form a clique, therefore the way that any cube of a path or cycle will sort of go is sort of they'll go through all 4 vertex classes in turn. And so what we are constrained by is precisely the size of the smallest set over here. So it turns out that for a graph like this, the maximum length they can hope for is of this form. And in fact, for if you want to find powers of cycles, you actually have a divisibility condition because you are constrained to having to go all the around in a periodic fashion. And so, for example, in this case, you only can get lengths of powers of cycles of which are divisible by 4. Right. So, so a little aside. Right, so a related problem here to finding a power of a cycle or path is one of finding a tiling of cliques of a certain size. So tiling is basically just a collection of vertex destroying copies of H in G. And to give here an example, if we have the square of a path on 10 vertices, how might I get a tiling of triangles? Well, I pick the first 3 vertices, those must be a triangle, the next 3 vertices also must be a triangle, and so on and so forth. So doing this, we basically, if you imagine for a long enough square of a path, you can always sort of get triangles like this, and it covers basically almost all of the path. Right, so in this, for this sort of slightly related but different problem, of finding these tilings, in fact, we have a resolution using the famous and rather difficult Semiradius theorem. So what it says is that essentially we can actually guarantee tilings which cover the number of vertices that you would expect in exactly this sort of construction over here. So these graphs sort of serve as the extremal examples for the related problem of finding a tiling instead of a power of a cycle or path. Right, so one might expect at this point, okay, these power-type constructions seem to come up a lot. Maybe they somehow govern also how these powers of path cycles would behave. So it turns out that we can actually construct a different family of graphs. And so how we do this is as follows. So we construct a graph, we call it G, P, K, and delta. What we do is we take K minus 1 independent sets, each of size n minus delta. So these correspond to these ones over here. And what we do with the remaining vertices is that we partition them as equally as possible, so that and to as many as possible, so that the resultant minimum degree will be delta. And where do we put the edges? We put edges between the independent sets, between the independent sets and the cliques, but not between the cliques. Is that okay for everyone? Okay, right. So and we denote by PPK and delta the length of the longest k-parallel path that we can find in this graph. Right. So how do these different constructions behave? This one versus the part one we had before. So here we plot for again k equals to 3, the length of the longest cube of a path that we can guarantee in the graph over the length of interesting minimum degrees, that is from 2/3 n to 3/4 n. So for the part construction that we had first, we plot here, it turns out to be this gray line, which basically extrapolates from sort of the point at which K4 appears and the point that we get a Hamiltonian cube of a cube of Hamiltonian path. On the other hand, for this different construction that we saw here, it turns out the extremal graph behaves like this. So it's a piecewise linear function with infinitely many jumps. And also the pieces themselves are actually flat, but they're actually slightly upward sloping. So these jumps generally basically correspond to when these values of RPs change, essentially. Right, and so the main result here is Allen, Böttcher, and Hladký were able to prove that if you gave me any graph and the degree in this interesting range, then you are able to actually guarantee for me a square of a path of precisely the length that you can find in this second construction that we had. And so they conjectured that indeed you can actually, in fact, you can actually generalize this to all powers of k. And that is sort of our main result is say basically, yes, we can. Right, so what will I do for the remainder of the time is to give you a sense of how the proof goes and what methods we use here, and also some ideas that it involves. So at a very high level, the methods that we use, is what we call the regularity blow-up method. So what this is basically it involves the joint application of two very powerful and breakthrough results. So there is Semiradius regularity lemma and the blow-up lemma of Hladký and Semiradius. And so using this sort of high-level method, what this enables us to do is to actually sort of reduce this original, slightly sort of more difficult, so the point is these powers of paths, they are really quite connected. You have to find all these linkages. But using this method, what you're able to do is to reduce it to a slightly different problem, where you just have to find these collections of cliques. But of course, you need some notion of connectedness, which is somewhat easier to tackle and hopefully will resolve the problem. And so what we need to do at this point is basically solve the reduced problem. Right, so to give you a sense of how this regularity blow-up method works, so the first part of it is basically this Semiradius regularity lemma. And so roughly, I can partition its vertex set in a way so that it forms a regular partition. But what does that mean? What that means is that you pick any two. So you took a graph, then you can partition it into these regular partitions. So what this means is you have a partition of the vertex set into more, but it's not always 3, such that the edges between any two blobs, or most pairs of blobs, what we call uniformly distributed. So what that means is sort of if you pick any two not so small subsets of these blobs, then the densities between these blobs are always not too different from the bigger blobs. So in this sense, it's sort of randomly distributed. Right. And so what we an object that we get out of this is what we call the reduced graph. So this encodes basically where in this partition we have not just regular pairs, but dense ones. So because a regular pair could actually be regular if it's very, very sparse, the density is very small, but those are not very useful for us. Right, so what we can say is that not just do we get a regular partition, but also one where this resultant reduced graph has a minimum degree that is sort of almost the same as the original graph itself. Right, so the other half of this method involves what we call the blob lemma, which was proved by Böttcher and Semiradius. And so roughly what this says is that if you gave me one of these things that comes out of Semiradius' regularity lemma and change a little bit, then they behave as if they were complete bipartite bits. Like here we have this regular thing, but so for purpose of embedding bounded degree graphs, these things behave as if they were complete pairs themselves. Right, so how would we use this? So, okay, so the first Semiradius regularity lemma gives us this regularity partition, which gives us this reduced graph that encodes where the dense regular pairs are. And now you're using what you get out of this, you basically use this, you try to find this, these collections of cliques, this reduced problem we have. And so once you are able to get that in the reduced graph, then you apply what we call the blob lemma. And what this, so the point here is that these powers of paths, they are bounded degree graphs. And so you can sort of embed them and sort of, for example, for the square of a path, you can kind of, the way you would do it is sort of you have these, for example, if you had a triangle which came out of the reduced graph, then what this corresponds to is essentially three clusters of vertices with regular pairs between them. And the way that you would embed these squares of paths is that you would first, put one vertex into, say, the first cluster, the second one into the second cluster, and sort of go around these clusters, embedding the vertices. Right, and so what this sort of corresponds to is essentially finding a embedding of a homomorphism from the target graph. So this, in our case, the square of a path or powers of paths, into the reduced graph, so that they don't actually overfill any of the clusters that we get out of the regularity partition. And because the reduced graph inherits this method minimum degree, so it essentially corresponds to trying to find these collections of cliques which are connected in a sense that I'll describe it later, that cover roughly the same proportion of vertices as we wanted for the power of a path. Right, so what is this notion of connectedness that we have? So here are a few definitions. So so using so now we'll use an example. Okay, so what is a KK plus one walk? It's basically a sequence of copies of KKs, so that every consecutive pair is essentially in the same copy of KK plus one in the reduced graph, in the graph itself. And so if we can find a walk between two copies of KK, then we say that they are connected in this sense. And so this sort of induces this gives us an equivalence relation, and so we get these notions of components out of the equivalence classes of this relation. And so to give you an example of how this would work, let's start from the edge 1, 2. and we want to say that there's a walk to the we form a triangle. So that allows you to sort of walk to the, so you can walk from T3 to T4 because the line in the same triangle, and so on and so forth until you from 4, 6 to 6, 7 using the last triangle. Four, 6, 7. Now, if you use graph of clusters that we have before, how would we the path of a vertices into this? So you put the first vertex into 1, the second you put the sixth one in here, but right, so now we are here. So this vertex must go into a cluster into 4, and now we have 4, 6, and we need to embed the last one, and that goes into single use graph, so that corresponds to a way that you can use it to embed these squares. So the aim now basically is to solve the reduced and so this is basically the lemma, which says that okay, we can actually solve the reduced problem. Right. So one case that we illustrate away is basically the case when you only have one of these components. So there's only one of them, and then we can just apply this high-mass Semiradius theorem right away, and that gives us a tiling which is large enough for the connect in the sense that we needed to. Right, so now we need to basically deal with the case of a component, and so here we will essentially it will actually involve two. One is essentially the notion of a pad construction. Right, so what is the interior? Vertices which lie in different components. Of the graph. So the thing is, these triangles in the okay. So we have side motion, and so triangles must only lie in one component, but its vertices could lie in many different components. We have this graph. Then the bit on the left includes another component, and so the interior of this graph would basically be the vertex 4, because this is 6 does lie in this other component, but 4 lies in triangle edges which are in both components. One of the main things in the proof is basically how do we construct these collections of cliques. That we want, and so the short answer is basically greedily. And so one of the things that we use here basically is the following. Lemma. So if you gave me some vertices in the graph with some minimum degree, then the common remaining see how this comes about is the first vertex has minimum degree delta, and for each of the remaining vertices, you lose at most n minus delta non-neighbors. So the common neighborhood is of this size. Right. So we need to strengthen this a little bit. In addition to the general setting, a set X such that some of the vertices and sort of the way to see how this comes about is basically you start off with one vertex with minimum degree delta. Before you have to lose n minus delta amount. Neighbors which are the vertex, but for some of these extra vertices, you don't have to lose all n minus delta. You get to lose sort of less, so n minus delta minus x, because they have common non-neighbors. Right. So how will we sort of use this to start building these collections of cliques? So the general idea here is we will sort of start from how to do that. So we will start with an extremal graph like this, right? So we want to build a from one component. So one way to do this is essentially to say, okay, we'll start from one of these, or anything they built from there is guaranteed to be the same. Component, right? So these extreme examples. So basically, what happens is it turns out that the components are basically then also one of the these cliques on the outside. So basically, the idea is that acquire a copy of K4, which cannot possibly be crossed because there are no edges in the middle. Right, so how do we construct these tidings? So we want to essentially break it up to get this. This is kind of